Hello, everybody. My name is Willem, and I'm the data science platform lead at Gojek. Today, I'll be talking to you about scaling data and ML with Feast and Apache Spark. So the agenda for the day, I'll give you a bit of background on some of the data challenges we faced at Gojek, why we decided to create Feast, the high-level functionality of Feast, and we'll talk a bit about how you can get data into Feast, how you can use it to train a model, how you can use it for model serving, statistics generation, validation, and a bit about the project and the road ahead for us. So what is Gojek? Gojek is an Indonesian super application. Today we're classified as a decacorn. We are focused on many different products and services. We have more than 15 products and services. We're most famous for ride hailing, cars, motorcycles. We have food delivery, one of the biggest food delivery networks in Southeast Asia, digital payments, logistics, lifestyle services. So the company has more than 500,000 merchants, restaurants, more than 1 million drivers. So the scale of our operations is very big in Southeast Asia. So given the product diversity and the scale of the organization, ML and data is critical to what we do. The most classic example is matchmaking, matching customers and drivers, but not just matchmaking, dynamic pricing, so search pricing, having machine learning models calculate prices across the whole, so all these service areas that we cover. So those are just two of the bigger examples. We also have routing, recommendation systems, for example, for our food product and food delivery, incentive optimization. We have supply positioning. So how do you make sure that the drivers are located in the right positions for trips to be started and to balance the supply and demand? And then, of course, fraud prevention. So given all of these use cases, and these are basically just the tip of the iceberg, ML and data is critical to what we do. And when we originally started, typical flow for a data scientist was something like they're given a business problem. They think in terms of notebooks and data and basically hacking something together. So most of our original use cases when the CS team in Gojek started followed this approach. Teams had an idea of going into production would require some kind of model serving, would require some features, and then be some integration with the production system. But for the most part, the focus was on what can you extract out of data in order to deliver value. So teams typically evolve these notebooks. They'll hack together a notebook, they'll iterate on that, and this is a very common practice, not just at Gojek, but across the industry. These notebooks evolved into Airflow pipelines or any kind of ML pipelines that are holistic end-to-end flows. You start with your data lake or your data warehouse, you're transforming your data. You can use Spark for that, Pandas, whatever you require. You use some framework like XGBoost or TensorFlow to train your model, and you somehow deploy that model into your serving environment. And in that serving environment, production system can integrate with you, and you can make predictions based on feature values that you're also persisting and serving. And this is kind of the approach that Gojek took originally, and it worked. You'd need to manage this whole end-to-end pipeline. You'd need to have some kind of system that can transfer the data that you've created in the batch pipeline into your production environment. Eventually, you'd also start, hooking up streams and transforming those streams and then populating your online stores as well as your historical stores with data. So for a holistic system, this works. This is fine. An MVP can easily be created that does this. But at Gojek, this approach didn't really scale for us. And I think at most organizations, this is great for a V1, but it doesn't really allow you to reach higher efficiencies and scalability. So some of the problems we experienced with this approach, this end-to-end monolithic approach, is one of the biggest ones was a lack of ability to iterate independently. So we had teams that would want to iterate on features, and we had team members that want to iterate on the modeling aspects, and then others that want to iterate on the models in production. So they want to either add new features, they want to experiment with different models and using A/B testing, or they want to just train new models. But all of these life cycles are independent, yet they're coupled extremely tightly if you evolve a notebook into an end-to-end production system. So that was one of the bigger pains we faced. Another pain we face is that code needed to be ported over from the training environment, because that's where it was being used for example, using Python to manipulate data and then train a model. It needed to be ported into the stream processing engines, or it needed to be ported over into the serving environment in order to create features. So this duplication of work was one of the pains that we also experienced. And the duplication of code led to inconsistencies, because now the data that you're receiving and serving is different from the data that you're using to train your model on. And that inconsistency can lead to data quality loss and model performance loss. And another problem we had was, because we were building these systems from the ground up, yes, you've got production grade infrastructure, but they're not built with ML in mind. They're generic data infrastructure. And so the quality and monitoring tools that are available are, it needs to be configured for your specific use case. And we needed to configure that in a way that made sense. And one of the problems with this approach is that the production engineers that are typically on call for managing these models do not really have the context of data that is being used in the model, and they do not know what is the right properties or shapes of data. And so this disconnect between the production side and the data creator side is one of the bigger problems that we also faced. And then finally, when you build these end-to-end monolithic systems, there's a deep lack of reuse and sharing of especially features. So you'll find that firstly, there's no knowledge of what is being used in these pipelines. So another team doesn't know which features are being created here. And if they do know which features are created here, they don't have a way to extract that data out of this pipeline, out of this whole flow. So that was one of our bigger challenges, is how can we avoid teams recreating these pipelines from scratch every time a new project is started? Because clearly spending 2/3 of the time creating features is not an efficient way to go about things. So Feast is kind of one of the approaches to solving these key data challenges with productionizing machine learning. Give you a bit of background about the project. Feast was developed in collaboration with Google Cloud and Gojek. It was developed at the end of 2018, and it was open sourced early 2019. So Gojek is the primary contributor there, and it's running in production using, for most of our large-scale ML systems, so our pricing engines, our matchmaking systems, many of the large systems within Gojek runs on Feast. Today, Feast is a community-driven effort. It has adoption at multiple tech companies, and some of these I've listed here. And these companies either are adoptees or they are contributors to the project. So if we go back to this original diagram, I think the question really is, how can we improve this monolithic approach to ML? If you introduce Feast, the stages of this pipeline are decoupled. So each of these stages, creation of features, training of models, serving of models, have a touch point with features, and they were all done independently. So Feast allows you to decouple them and iterate independently. So if you're a data creator, and this might still be the same data scientist, you're creating features either through processing a stream, either through processing your batch data in data lake, or your batch data in a data warehouse, or even just a CSV, but that data ends up in Feast. And that's where that specific iteration cycle ends. When you're training a model, you're not processing your data from scratch. You're not retransforming raw data. You're selecting data from the feature store. And so that's where kind of this decoupling means that there's no strong relationship between the person training the model and the person creating the features, although normally in projects, those are the same person. But this decoupling allows the person creating the model for training to select any amount of features from any amount of teams throughout the organization. So this is very powerful for us to make it possible for teams to iterate independently. And so when you're training a model, it's mostly a matter of selecting the features that apply to your use case, and then creating your model binary and persisting that in a model store like MLflow. So what teams typically also do is they store a list of features. These are the lists of features, or feature references as we call them, that were used to train the model. with that model binary, and then they ship that into the model serving environment. So in model serving, you're loading your data from this registry like MLflow, you're serving it into your production environment, and all you need to do to get the same data to that model is send another request to Feast for online values, and Feast will return those to you. So here you have three stages that are not decoupled, and you can iterate on them independently. And what you'll find is at scale, you'll build up a base of features that are reusable across projects, and you'll automate your production serving environment. So all of the focus goes into the modeling environment. And so that's where the data scientist spends most of his time instead of crafting features from scratch over. So what is Feast? So in summary, Feast is an ML-specific data system, and it attempts to solve these ML-specific problems. So I highlight that aspect because if you're only focused on data storage or stream processing or any one of those aspects, none of those are ML specific, but there are specific constraints to running ML in production, like the consistency between training and serving that need to be upheld. And so Feast can be seen as an opinionated configuration of production data technologies in order to serve these ML needs. So for example, Feast allows you to consume from multiple sources, so either batch sources or streaming sources, and it stores those, persists those in a way that it can be served in a point-in-time correct way later for training your data, for training your models and for serving, for model serving. So when you're ingesting data, it stores the data in online stores, it stores it into historical stores. Feast allows you to standardize the definitions of features. So as a data creator, you define entities, you define features, and you map this into the data that you create. Then as an organization, you have a standardized definition of those features that you can reuse across projects. And this encourages reuse and sharing because now you also have, with Feast, a single canonical reference to each one of those features. And so you're not talking about, look at this CSV, look at this column, or look at this key in this database. Look at this query. You're talking about a name of a feature, this reference, and that's all your model sees. It doesn't see the implementation details of the infrastructure. Feast allows you to ensure consistency between your training and serving environments through that abstraction. And Feast ensures that the data, and partly through the ingestion layer and the way that it stores data, it ensures that the training and serving layers always receive the same data. So the model is trained on the same data that it'll get in serving, and that ensures that the performance of the model is upheld. Feast is also able to do a time travel or point-in-time correct query of your features for producing a model training data set. This is a critical aspect of creating training data sets that a lot of data scientists do today, but is quite error prone. If you do this incorrectly, you're either going to have stale data that you're serving your training model for training, or you're going to leak data from the future to your model. And in both cases, the model will perform badly, and it will be very hard to debug and know that there is a problem. Feast is also able to allow data creators to define schemas, and these schemas can be used based on statistics that Feast generates on the data to validate the quality of your data. So if there's a data shift, Feast can let you know that something is wrong, and it can prevent you from shipping a bad model, or it can prevent you from continuing to serve a bad model or a good model and bad data in production. So what is Feast not? So Feast is not a workflow scheduler. It's not a pipelining solution. It isn't a warehouse, though it is a storage system for data. It abstracts the warehouse lake or online stores, but it's not just a database. Feast is not a transformation system, so this is a very key point. Some of the other feature stores have transformation capabilities as the key value add. For us, we consider existing tools to be a better solution to these problems. So we try and focus on the other aspects of other challenges to productionizing ML. So we encourage the use of Spark or Pandas in the upstream systems, and then we become the productionization layer. Feast is not a data discovery or cataloging system for your whole organization. An aspect of what we do is feature discovery and reuse and cataloging, but that's a subset of the data that's available in your organization. Feast is not a Git for data or data versioning or lineage system. There are tools and products that do that, We might integrate with those, but they're solving a different kind of problem to what we're trying to solve. Feast is not a model serving or metadata tracking system, so we produce artifacts and we produce metrics that can be tracked in those systems. But we do not serve models. When you serve a model, because the model is ultimately a transformation, you can produce data as an output to the model that gives back into Feast. So you can use Feast to track statistics about the models and to actually use the schema validation to see if your models are drifting from their traditional outputs. So in some ways you can integrate with model serving, but it doesn't serve models itself. So let's talk a little bit about how you can get data into Feast, how you can define features and entities and schemas. When you're working with on ML systems, typically what you're trying to do is you're trying to predict some kind of event, some kind of phenomenon on an entity. So the entity can be a customer, it can be a driver, it can be a booking, an order. You want to make some kind of prediction, and you do that through features. These features are attributes or properties about that entity or about any entity in the environment or world that you're operating in. So a key concept in Feast is definition of these features and the definition of these entities. So the feature set is how you do that. On the screen, we have an example of a feature set, the driver weekly feature set. This feature set maps onto one table that we've shown there in green and yellow. And this is a table that represents drivers. So on the left, you can see driver IDs. You can see there's a conversion rate, an acceptance rate, and an average daily trips. And so this is these are batch features. They're calculated on a daily basis. So you can think of the feature set as a kind of bulk way to define sets of features that occur together. And importantly, these all occur on the same timestamp. So they're computed as part of the same aggregations. And these features, I think it's a very important thing to note is that a feature set is an ingestion concept. It's a means of defining a schema on how data will be loaded into the system or data will be sourced by Feast into the system. It's not a means of selecting features for training a model. It's only a definitions grouping. So here's an example of ingesting data into Feast. So what we're going to do is we're going to take that existing data frame that we showed in the previous slide, load it in as a CSV, the driver weekly data CSV. We're going to define a feature set. We're going to infer the entities and features from that data frame. And then we have an object, that a Feast object, a feature set object that we can apply. And the apply step essentially registers that feature set with Feast. So now Feast has an idea of that entity, the type of the entity, and the features that are associated with that entity. So the final step there is ingestion. The ingestion step loads the data into Feast. The important thing to note here is that once you ingest that data, depending on the subscription of the stores that are inside of Feast, the serving layer, those stores will all immediately be updated with this data. So when you do an ingestion, all of the online stores immediately get access to this data, and they have the data available to them in a point in time and consistent way. But Feast is also capable of ingesting from streams. So in this case, there's a subtle difference. We're defining a driver stream feature set. On the right, you can see an example data frame of this event stream. So you'll see there's a trips today feature, the one in the column in green. And these are just events that are coming in on different kind of driver IDs on some kind of stream. And the topic is the driver stream topic. So what happens here is that you're defining a feature set, you're registering it with Feast using the apply method. As soon as you do that, Feast is going to provision a ingestion job. This ingestion job is going to start streaming in the data, and it'll make sure to populate all of the stores that are subscribed to this feature data. And this is kind of the high level architecture of what happens to that data. So if you look at the 5 stages here, you've got your data. You can think of that first layer as kind of the raw layer. It's your existing streams, your existing warehouse, data lake, or just your notebooks where you're doing iteration. That's the area where you're working with your data. Then you have a ingestion layer. This ingestion layer is going to take data from wherever you've created it and populate stores. And these stores can be either historical stores used for creating training data sets, or they can be online stores. An aspect of what actually happens that's not really shown here is that there's a streaming layer that populates online stores. And so that streaming layer allows you to have as many online environments as you want. So if you have a large organization, they can have their own independent serving environments that just tap off of a stream, and their stores automatically get populated when anybody loads new data sets or streams into Feast. Your serving layer is the fourth layer, and that's the way that teams will interact with the data that's persisted within Feast. So a model training pipeline or a model serving system could send a request to the Feast serving layer, either for a point-in-time correct training data set or for online features, and Feast will export that or return that at low latency. All of this is managed through Feast Core. Feast Core is, you can think of that as having a dual purpose of being a registry. It's the central place where you define features, define entities, define feature sets. It allows you to search and discover these features. It allows you to track metadata and attributes and the properties of those features. And Feast Core also allows you to generate statistics. An important job that Feast Core does is it manages the ingestion there. So when you register feature sets, Feast Core is the one spinning up the jobs and ingesting the data into these stores. And so this is a kind of high-level view of how Feast takes data, stores it in a way that is consistent. And the reason it's consistent is because the ingestion layer writes to all of the storage locations in one go. So that ensures that at no point in time do these stores become inconsistent with each other. So that unified storage is a key aspect of what Feast does. So once you've stored your data inside of Feast, feature serving is the next important thing to look at. So here we have two loops. If you look at the right, there's the model training loop and the model serving loop. For training, what you want to have is a training data set, and for serving, you want to have, just the features that you need to do a prediction. But there's one thing that the model always needs, and that is the data should be in the correct format, a consistent format in both cases. And Feast helps with this by abstracting away kind of the infrastructural aspects, the implementation details. And so the only API contract that the user needs is the feature reference list. So feature references are canonical references to features stored within Feast. An important thing to note here, and if you look at this feature list, is that they're based on the two feature sets that we registered. The reason that's important is because you can reference features from any amount of feature sets. As long as a feature is referenced in Feast, you can reference it. So you can send a request to Feast serving, either for a training data set or for online serving, and Feast will build a training data set. It will do a point-in-time correct join and stitch together the data to produce that training data set. The only requirement is that you have the correct entities to join that feature data onto. So in training, you're going to send Feast a list of entities, so driver IDs and timestamps, and then Feast will join the data onto the feature data onto that. And in serving, you will send just, for example, the driver IDs, the list of features, and then Feast will send back the feature values attached to those driver IDs. So in online serving, you're only getting back the latest data, but for historical serving, it's giving you a point-in-time correct view of the data for training. So one of the key value adds here is that is the consistency between these environments, and the fact that the historical data sets represent the point-in-time correct view of the data. An important thing to talk about is this point-in-time correctness and kind of the events that happen throughout the life cycle of a project. So if you look at this timeline, the green diamonds are essentially feature values that are being computed. That can be during, batch transformations or streams. It doesn't really matter, but essentially at some point in time, a new value is populated and it's ingested into Feast or it's streamed into a store and it becomes available. The red square is an event in the production system. So that's some kind of event that mandates a prediction. So that can be like a booking is made or some kind of transaction is made and you need to make a prediction. And the final purple square is the outcome. So that's the final event that happens, or the final data point that arrives that tells you whether it was a success or a failure. So these three colors represent the three types of data that you deal with when you're building an ML system. And you need all three of them to be able to train a model and to be able to know the outcome of a model and to have the correct labels also to train that model. So if you look at this view, if you're doing a prediction online, so that let's assume that at that rider booking event you want to make a prediction, you have your model already. What you want to do is you want to provide the correct feature values. So for each of those four green rows, you're going to send the latest values to your model. That's very easy to do in online serving. All you need to do is make sure that the latest values are available and that they're not too stale. So you always have the point in time correct view of the data in online serving. But how do you do that for historical serving? This is very tricky to do because these timestamps don't line up perfectly. So if you have many different booking events and you have many different labeling events or outcomes, and all of your features are calculated at different timestamps, producing this training data set is non-trivial. And this is something that is a requirement for data scientists to do. And it is an extremely error-prone and can be often a complex task for them to undertake. So this is something that Feast does natively. It allows you to stitch together the data based on its source, based on its update rate and frequency. All of that is abstracted away from you. It'll produce a point-in-time correct, time-traveled training data set for you, regardless of at what time the data points were updated. So a quick example here is using our existing data frame of driver features. So on the right, you have a new data frame with some labeled events. So these are basically just has the trip been completed successfully or not successfully. Those are the target values that you want to join onto. And on the left, you have features and driver IDs. And so if these were two data frames that have been loaded into Feast and you query this out, you could produce this final training data set. And it doesn't matter whether the timestamps don't line up. Feast is able to, you can indicate to Feast that the one table is your basis table, the table on the right, and the one on the left is the features that you want to join onto it. And Feast can ensure that it's joined in a point-in-time correct manner. So here's this code snippet using our Python SDK and how you can retrieve feature values from Feast for training model. So on the left, you have your list of features. Those are the feature references. So those are the canonical references that I spoke of earlier. So this is all you need to pass to Feast is this list of features, and then you want to pass the entity data frame to Feast as well. This data frame contains driver IDs and timestamps, and those typically are mapped straight onto the timestamps that the events occur for prediction. And so you send that as a request to Feast. Feast returns a data set that can be materialized into a data frame, a pandas data frame, or it can also just keep the data frame persisted on disk or in an object store. But essentially what it's going to do is produce this final training data set based on feature sets, multiple feature sets. So if you look on the right, you have two different categories of feature data. You have the batch data that we ingested originally, and we have the trips today streaming features. And so it's irrelevant where the data came from, at least in the eyes of Feast, because it can just join these in a point-in-time correct way. But it doesn't matter that the one's coming from a stream and the one's coming from batch. So Feast can join all of this together for you and prevent the typical errors that occur, like leaking feature data or joining data together in a way that propagates stale data to your model training. So a team would typically produce the data frame, they would train their model, and then they would persist their model binary with a list of features. So here we have an example of going to production. So this is the Python SDK, and you'll notice that the list of features is identical. So you don't have, a Spark query or a SQL query in training, and then you have some kind of different database used in serving. The only difference here is the method that you call in online serving, but the list of features is consistent. And that's kind of one of the key value adds that Feast brings, is that the list of features, the feature references unify both environments. So in production, you'd have driver IDs. These are your entities. You would not have timestamps because you're always requesting the latest feature values. So you'd send the list of features with driver IDs, and the Feast would attach the latest feature values that you then return. So in this case, we're only asking for one driver ID's features, but in reality, you'd ask for, let's say, 100 driver IDs or more. And the Feast would give you these values at low latency. So our current stores operate in the single-digit millisecond latencies for this. And operating at scale is really one of the requirements that we have. We also have JVM and Golang clients. So this Python client is basically just shown for illustrative purposes. Feast is also able to allow you to generate statistics and use those statistics to generate schemas, and then subsequently use those schemas across training runs or as well as in production to validate data and prevent data shifts from occurring. So here's an, so Feast integrates with TFX. Feast has interoperability with TFX through its feature specifications. So TFX and TFDV are tools developed by Google that allow you to define schemas on data sets. And these schemas can be used for validating data. We felt that these were great tools and we didn't want to reinvent something that already existed, but we wanted to complement them. And so that's why we integrated those schemas into our feature specifications. So Feast is able to generate statistics that are compatible with TFDV. So once you load your data into Feast, you can export these statistics in a TFDV compatible format. You're also then able to use those TFDV schemas to do validation of the statistics. And you can do this during training runs, and you can do this during at ingestion time as well when you're streaming data into your stores. And Feast is also able to integrate with monitoring and alerting systems. So currently we have integration with Prometheus. So our ingestion pipelines can produce metrics and statistics, and these statistics can trigger alerts based on schemas that are defined upstream. So these schemas are defined based on the properties of data by the data scientist. And I think this is one of the key values. This is why we wanted to integrate TFDV and TFX into Feast, is because the data creators know the most about the data that they're publishing or authoring for consumers. They have the domain knowledge. It's important for them to be the ones defining the schemas that ultimately will be used for validation. And if we only limited this to TFX or TFDV, it would be a batch. It would be a siloed batch process that happens in a single pipeline. By incorporating this into our feature set specifications, we can apply those schemas not only for training, but also for serving and ingestion. So throughout all the touch points that features occur in your organization. Here's an example of inferring schemas from existing features and then registering that with Feast. So the first step there, we're generating statistics based on an existing iris feature set that is within Feast. That statistics object that is returned and calculated the computation is all done by Feast. Behind the scenes. So it abstracts away the infrastructural and computational aspects. But the schema of the statistics that's returned is 100% compatible. In fact, it is a TFDV schema that's returned. It's TFDV statistics that's returned. Those statistics can then be used to infer a schema. So that's all happening client-side, outside of Feast. You can then use the normal TFDV approach of tweaking the schema and setting the values, and then you can so what we want to do is, once you've defined that schema, you want to update the feature set that you're working with in order to enrich it with the schema. So we're going to retrieve, using the get feature set method, the feature set. We're going to import the schema into that feature set, and we're going to re-register it using the apply method. So the apply method is an idempotent update method for that feature set. So we're re-registering that iris feature set with Feast. And if you look to the right, you'll see that now the iris feature set has not just the name and the value type of the feature, but also presence, min fraction, min count. So these are TFX, TFDV properties that can ultimately be used to validate those features. And the schema can then be used for not just for validating training data sets, not just for validating ingestion or serving, but it can also be used to indicate the intent and the properties of that feature. And an important thing to know here is that when you're registering these properties about these features, you're doing it on a feature by feature basis. So even though they're grouped together here, when they're used, ultimately they can be used across feature sets. So here's an example of creating a training data set and then returning statistics and a schema from the training data set. So this is going back to our previous example of the driver-based features. So you're sending your driver entities to Feast, you're sending a list of features, and Feast is going to return a data set. But For statistics and validation purposes, Feast will also return a pre-computed statistics based on the data set that has been produced. So for that exported data set, it will run a TFDV compatible operation that produces statistics. And it will also provide the schemas that have already been registered on those features. So remember, now you're picking features that are crossing feature sets. It's any kinds of driver features in the organization you can pick from. And it will propagate the schemas that those feature authors created. And it will return that with your data set. So you can use TFDV client side to validate the data set that you're going to use for training your model prior to training. And you can just use TFDV to detect those anomalies. Because we are using TFDV, you also benefit from being able to use facets. So facets illustrated on the right using that UI. So you can just generate the statistics and visualize it for basically for EDA or for debugging purposes. So what are the key takeaways from incorporating Feast into your lifecycle of ML? So the key value adds of Feast are, with sharing, teams can now start with selection instead of creation. They can quickly get up to speed, focusing on the ML aspects. On iteration, they can independently iterate on different aspects of the different stages of the life cycle without having to be stuck on a monolithic approach. They can focus on independent aspects. Feast provides consistency between training and serving and ensures point-in-time views of your data. Feast allows for centralized definitions, and it allows you to reuse features throughout different projects. Feast also ensures the quality of the data that you are producing, and it allows users to encode, or data scientists to encode their knowledge into those schemas and to ensure the quality of the data that ultimately reaches your models. So finally, the road ahead. So Feast 0.6 is landing soon. It's landing in June of 2020. With that, we'll have statistics and validation, improved discovery, and metadata functionality. The community is currently developing Databricks support, Azure support, AWS support. We have BigQuery SQL sources landing soon, JDBC connectors. We're looking at developing a derived features system for online serving, as well as a user interface and allowing for automated training serving skew detection. So we encourage you to get involved. There are some links to our open source project. We're on the Kubeflow Slack channel. You can have a look at our mailing list and join that if you want to find out more. There's a link to the slide deck. And yeah, that's it from my side. Thank you.